Published in the recent domestic peer-reviewed Science Bulletin, scientists from Shanghai, China, report that they have developed a new powerful cooling system for the most demanding quantum technology to create supercold temperatures that would make cutting-edge technology such as quantum computers more widely available. And this new cooling system is not using any helium-3 at all like an actual quantum computer. The new cooling system uses helium-4, another helium isotope, as its coolant. The core components of most quantum machines, from quantum computers to quantum devices of satellites, detect and manipulate subatomic particles that are easily disturbed by heat, so must operate in conditions near absolute zero. Cooling the most advanced quantum hardware requires helium-3, an isotope of helium that can carry heat away with unmatched efficiency. But helium-3 is scarce on Earth, and the main supply is from aging nuclear warheads. The demand for helium-3 in quantum research and other disruptive technology has soared. In less than 2 decades, its price has risen more than 40-fold. But even then, not just anybody can buy it. For instance, in the United States, helium-3 is one of the few commodities subject to strict government controls. Helium-4, the gas that goes into party balloons, is much more plentiful than helium-3 but is less effective as a cooling agent in extreme conditions. When approaching temperatures as low as 2 Kelvin, (-271 degrees Celsius), helium-4 turns into a superfluid, climbing walls regardless of gravity and becoming much more difficult to control. The Chinese research team has developed a theoretical model that could, to some extent, predict the behavior of helium-4 flow in a superfluid state. The new cooling system is similar to a household fridge but has few moving parts. It is driven by a pulse energy source and operates at a high frequency to increase heat transfer efficiency. The new cooling system has a particular component to stop the anti-gravity climb. According to the researchers, part of the device must also be built with exceptionally high-quality components with precision twice as high as mainstream products today. In their experiment, the new cooling device kept a superconducting nanowire single-photon detector, an optical sensor commonly used in quantum machines, at a temperature of 1.8 Kelvin for more than 2 weeks, 15 days. The results suggested that the helium-4 had the potential to completely replace helium-3 even in some most demanding applications, such as space missions, said the researchers. Using helium-4 would help remove a significant constraint to the mass application of quantum technology. China has made a significant contribution to the development of quantum technology in recent years. Chinese researchers have built the world's first quantum satellite, most extended quantum communication network, farthest-ranging quantum radar, and fastest quantum computers with government funding. These developments used a superconducting nanowire single-photon detector, SNSPD, cooled by helium-3. The figure shows the relationship between detection efficiency and dark count of SNSPD devices with bias current. The figure shows the new cooling system. The figure shows the typical cooling curve of the new cooling system. The researcher team has now launched their own startups to speed up the commercialization of the research technology with a mix of government and private funding.